All right. Well, what should we talk about? I know I have to constantly entertain you with new and fresh material. I feel like a stand-up comic sometimes. You can't just keep telling the same old jokes. Okay, where were we? Well, uh, okay, let's see if anybody can name the subject we've been talking about the last couple of. Grail. Okay, what have we concluded? Can we move on, or have we extracted every last bit of meaning and mystery from the symbolism of the Grail, and now there's nothing more to say about it? So we should just move on to the next topic of the week. Okay, so I do have a little bit of news. Me and Brad got our plane tickets today, and we're going to head out to we're heading out to Kalispell, Montana. We were hemming and hawing about going because we wanted, we've been talking about wanting to go to British Columbia, and I don't know if you guys remember about 2 months ago, 3 months ago, when we were talking about the Ice Age Floods Institute is sponsoring a field trip led by geologists, and I don't know which geologists, but this is the one we went on last year in August or early September. And it was also led by 3 or 4 geologists that have been studying the Missoula Flood out there. But where the field trip is going this year is outside the normal bounds of Missoula Flood effects. And it's a place where Brad and I have gone at least twice. In fact, one of the overflights that we did, in fact, I should pull this, in fact, this photograph right here was taken on an overflight last summer as we're up in the very region where this field trip is going. And the reason we have gone up to that region and then went back again is because there is major evidence up there that totally contradicts the prevailing paradigm about the Missoula Flood. So I have no idea of what they're going to be looking at up there, but I felt, well, here they're following basically the trail that we already blazed on 2 different occasions. What was the first year we were up there? 2002 or 2001? Yeah, so there's major evidence up there that and I think what we're about to see, I think it's happening now, is that some of them are beginning to question the orthodoxy that's been in place for the last half a century. And the significance of that is because as soon as they begin to question it, then they're going to realize that what they're looking at is a much bigger, much more profound event than orthodoxy has allowed it to be. And once we get to that stage, then I think we're only like one stage away from the recognition that what we're seeing up there is the effects of a global event. And I have gone to 2 now. We're joining the Atlanta Geological Society because I've gone to 2 meetings, or a meeting and a class. It was a class held by a glaciologist last weekend. So I wanted to find out. I was going to question him and try to, fill in the blanks in some of my knowledge about what goes on with glaciological processes. But I guess the main problem was that I don't think he really knew any more than I already knew. So I in fact, probably less about some aspects of it. So I did talk to him, though, and somebody else about perhaps addressing the Atlanta Geological Society, which is basically an organization of all the professional geologists in this area, which will be a first. I've never presented. I mean, I always present this material to, mixed groups, and so I can't really get into the level of technical detail that would, if I do that, pretty much it puts everybody to sleep. But a professional geologist presumably should be able to follow the scientific arguments. So this could be a milestone, actually presenting this story to a group of professional geologists for the first time ever. I mean, I've certainly presented it to individual geologists here and there and have elicited some interesting responses from them. But this would be the first time. And what I'm convinced of course, is that the people here in Georgia are not really familiar. Most geologists will have heard of the Missoula Flood, just like, of course, most geologists know that, the dominant theory for the extinction of the dinosaurs was an asteroid impact. Although they may not know the details of it, the specifics of it, they certainly know that. They're aware of it. Most geologists are aware of the Missoula Flood. But if you ask a geologist to tell you what it is, they'll pretty much give you the textbook explanation that's been around for half a century that quite frankly doesn't make any sense. And nor does it explain a whole host of related phenomena, including stuff that's in this region right here. You can see this is Flathead Lake right up here, the southern end of Flathead Lake. And right where we are here, we're flying over what would have been the what's called the Outwash Plain on the southern margin of a glacier. As a glacier is receding, all kinds of sediment-laden water discharges in a big sheet over the land, and as the water spreads out and slows down, it leaves this huge thick layer of sediment. And that's what the modern Flathead River has entrenched itself into, this like 300 to 400 feet thick layer of sediment that was laid down in the wake of this massive meltdown. And see, that's what it is. We're looking at, we've talked about that in here, and you know, the whole, if you remember, the energy paradox is the idea that this event, the melting, was accompanied by an injection of energy into the terrestrial system that had no really known source. Because there was no terrestrial energy, no source of terrestrial energy capable of achieving that kind of effect. And so the energy paradox was first discovered in the early 70s, when they began to think that the ice disappeared in 10,000 years and not 30 or 40,000 years. And when they thought that the ice could disappear in 30 to 40,000 years, there's enough energy available. We had a little ice age that we were in for 400 years. During that little ice age, from about 1350 to about 1400 to 1800 or 1850, depends on where you look, but there was a period of global cooling. It caused glaciers to expand worldwide, and in fact, to some glaciologists that have looked at it, they think it was the biggest expansion of glaciers since the Big Ice Age that ended 10 to 12,000 years ago. When the Little Ice Age glaciers began to recede between 1850 and 1950, what we saw was that they receded without necessarily causing catastrophic flooding. That's the key of the whole thing. They essentially, you could go and watch them recede several feet a year, as they've been doing consistently now from about the mid-1800s down to the present. When you see somebody coming up and talking about, oh, the glaciers have shrunk, and they show you a picture, say, of the glaciers in 1960 or 1970, and then a glacier, the same glacier now, just remember that that process of contraction actually started over 150 years ago. And it was starting from the largest the glaciers had grown globally since the Big Ice Age. So it's somewhat disingenuous to say, you know, that to just then conclude from that the only or exclusive effect causing glaciers to recede is human influence, because in 1850 to 1940 it's acknowledged that there was no significant increase in CO2 caused by human activities. But the glaciers did most of their recession between those years. What we see now has been an ongoing process since the middle 19th century. And again, it started out from glaciers being the largest they had been in nearly 10,000 years. So, but what I'm getting at is, with that contraction of the glaciers, a lot of streams were carrying lots of, you know, they were augmented with a lot of meltwater. So a lot of streams were carrying more discharge than they would have been carrying while the glaciers were expanding, say from 13 to 14 to 1500 years ago. They were also carrying a lot more sediment. When the glaciers pulled back, they created a whole suite of landforms, such as moraines and erratic boulders and stuff, that allowed the natural philosophers of the 16 and 1700s and 1800s, early 1800s, to witness firsthand the effects of first glaciers growing, how they modify the landscape through their growth, and then contracting, and how they in turn modify the landscape as they contract. Once they saw that process happening real time in front of their eyes, they saw the building of moraines. They saw the formation of eskers, or sinuous mounds of material that were actually flowing through in tunnels through the glaciers. When they saw the large boulders left behind, what that did was it allowed them, it gave them the eyes to then see let me put it this way. By recognizing the effects of the Little Ice Age, it gave them the eyes to see the effects of the Big Ice Age. Coming down off the Alps, there are valleys that go to the northwest towards the Jura Mountains, which are about 30 miles away. The Jura Mountains are to the Alps much as the Appalachian Mountains are to the Rocky Mountains. They're much lower. They're much more eroded down, so they're not the sharp, young, orogenic features like you see in the Rocky Mountains. During the Big Ice Age, all the glaciers over the Alps grew down, completely filled this 30-mile valley between the Alps and the Jura Mountains with ice. And it carried granitic rocks whose source was from the Alps, carried these boulders over and dropped them in the Jura Mountains, which I believe were a type of ancient sedimentary carboniferous rocks. They were very distinct. In any case, the granites came from the Alps, I think it was, or maybe it was vice versa. And anyways, the erratics were very distinct rocks. So people had noticed these and had attributed those to the effects of Noah's flood. Okay, so now the Little Ice Age comes along. The ice expands down from the Alps. It does in miniature the same thing the Big Ice does, only instead of carrying the erratics all the way across this 30-mile valley separating the two mountain ranges, it brings the erratics down to the foothills of the Alps, maybe 5 miles from the base, and dumps them there. So now they look and they see the erratics, and they see the moraine, the jumbled rock, piles of rock and debris that's shoveled up in front of the glacier as it advances. Imagine a bulldozer just pushing up a pile of stuff. It stops, and then it just goes into reverse, and it leaves this pile that you can look at and go, okay, this is how far the bulldozer came. That's essentially what a glacier does, and it leaves this arcuate form of this till, it's called, or in the old days, drift, when it was still believed to have been emplaced by Noah's flood, this jumbled stuff, and it marks the limits of the glacier. And then associated with that will be these large erratic boulders that were quarried by the ice, and beyond it then will be this outwash plain composed of this fine sedimentary material like you see right here. So all of these features that the Big Ice Age created were recreated in miniature by the Little Ice Age. So they were able to go out and see firsthand these features of the Little Ice Age, and then finally figure out that, hey, these granite boulders here on the Jura Mountains are exactly like these rocks over in the Alps. And look, here's this jumbled stuff that contains material from the Alps. And they soon figured out that the ice had once been many, literally thousands of times greater. The glaciers of the Alps had been thousands of times more massive. And that was how they came to understand the Big Ice Age. So what they did was they used the present as the key to the past, and hence was born the concept of uniformitarianism, by looking at the present, trying to decipher events that happened in the past. And it became a very, very powerful tool for understanding past processes that were essentially no longer operational. The problem came in when uniformitarianism became a dogma. And anybody who then proposed that, well, wait a second, things sometimes have happened that weren't at the modern rates. Modern rates we've been told, are slow. One drop of water, geology changes one drop of water or one grain of sand at a time. And this is what we were taught. Anybody who went to school in the post-World War II era, from the 50s up to probably even the 80s, was taught that. You know, in science class, when we had our 2-week section on Earth history, we would see a film or read in our textbook about how geological change happens over many millions and millions of years. And if we got into it a little bit further, we were taught about the concept of uniformity and how geologists would study things going on today and then extrapolate to things going on in the past. Well, it turns out that the concept of uniformity works the other way too. It not only tells us about things, modern correlations to things that happened in the past, it tells us when things happened in the past that have no modern correlations, no modern historical analogs by which we can say, yeah, here is this thing happening, and it's the same as this thing that happened 1 million years ago, or 100,000 years ago, or 100 million years ago. Certainly, there are catastrophes in the history of the Earth. And I tell, if somebody asks me, my philosophical point of view, I say I'm a catastrophist. I believe there's two modes of change. There's the type of change that we generally go through day to day in most of our lives, but even using a single human life as being an analogy to a greater cycle, you know, everybody, sometime in their life, you have a catastrophe. You know, you fall off a ladder. You go through, you know, day after day and nothing much happens, and then one day you fall off a ladder. That becomes a catastrophe. And what happens during those few moments, you're in a car wreck, you know, whatever. You can come up with a thousand different things that could happen, but the key, the idea is that within that limited small amount of time, more change happens in effect. I mean, if you fall off a ladder and break two legs, you know, what happens during that period of time affects your life as much as, you know, several years of life, normal life put together, or more. And it's the same way when you're talking about the life of a planet or the life of a world. It's the catastrophes that basically set the whole direction of evolutionary change. And catastrophe is now becoming finally recognized by modern thinkers, as it was by ancient thinkers, as being the dominant process. You know, just like they say in warfare, you know, it's long periods of boredom separated by short periods of terror. Well, that's the catastrophic model of Earth history. And even though we may like to think that, you know, it's a long, slow, pleasant ride with maybe a regional or a local event here and there to upset the order of things and the placid pace of change, the reality is that there are periods of concentrated change where within a matter of a very short period of time, there's many times more change than there is in these long intervals of quiet in between. And that's essentially a catastrophic model. And once you begin to think in terms of a catastrophic model, the catastrophes have left their fingerprints all over our planet. Going back to we certainly see them going back to the very beginnings of life and beyond. The bombardment period that culminated the formation of our planet was violent beyond really anything we could even begin to imagine. The birth of the moon must have been incredibly traumatic. That's a subject we definitely need to come back to also, the moon, because it's very, very important, and I will have a program I'm going to do on the moon. But coming right down, we see that the history of life has been a history of great catastrophes, where life is going along smoothly and then something interrupts it, and there's a whole nother level of stuff that happens. Well, 12,000 years ago, something, and we can only presume, I only presume, we have to look outside the system to find the source. There was an event that basically precipitated the end of the Ice Age. And all the scientists that have looked at it, the climate scientists who've studied it from this angle, would agree that once an ice age is in place, it almost should be completely self-perpetuating. And why would that be? Why would an ice age be self-perpetuating?
Albedo effect.
Albedo effect. What's albedo?
The white reflecting the sun back below.
Very good, Harvey. Yes. And the albedo change is very significant. What happens is, as the ice expands, ice is light-colored, it's white, it's highly reflective, and it reflects a great deal of heat. And it reflects the heat, enough heat away, so that the area peripheral to the ice sheet stays extremely cold. Well, what that seems to imply is that an ice sheet should be perpetually growing because it's cooling, constantly cooling the region where it's at. And in fact, there's evidence now during the Ordovician maybe that there were at least one episode where there was a runaway ice age, where whatever feedback mechanisms have constrained ice ages weren't working. And the whole planet became frozen, even to the equator. Have you heard about that? Yeah, even to the equator. The whole planet became frozen. And that would be, in a sense, that would be the logical outcome of an ice age. But there are obviously other factors involved that restrain that process, because we've been through perhaps 40 glacial and interglacial cycles since the Pleistocene began 2 million years ago. And we don't still, there's no consensus or really comprehension of what triggers the onset of an ice age in the first place. And then secondly, once we're deep into to the state of ice age, what brings the Earth out? You know, how do we go back, say, 26 to 30,000 years ago to a climate probably not much different than now, and within a few thousand years, the Earth has completely shifted modes, and now you've got a massive expansion of ice sheets around the planet to the extent that all of Canada is swallowed up in ice, all of the northern United States, all of northwestern Europe is swallowed up in ice. High mountain ranges all over the world, the Himalayas, the Andes, the Rockies, the Pyrenees, they're all swallowed up in ice. Sea levels begin to drop down, and they drop 400 feet worldwide. As they drop, they expose millions of miles of now newly uncovered land that had previously been shallow marine ecologies underwater. They're now exposed. The changes that are wrought upon the planet's surface are profound at the onset of an ice age. And probably since we humans have been here, we have experienced a minimum of 4, possibly 6 or 8 transitions into ice ages and out of ice ages. And the problem with catastrophism, one of the problems is that once you recognize the footprints of catastrophe, see, the problem is that when you have a great catastrophe, it so completely rearranges and changes what came before that it oftentimes erases the footprints of the earlier catastrophes. One gauge that we can use to try to determine the severity of a catastrophe is what effect does it have on life? What effect does it have on the biosphere? 12,000 years ago, there was a major effect on the biosphere. In fact, you could put it this way. It's not unrealistic to say that 12,000 years ago, the top of the food chain was decapitated for the most part. I mean, this happened. The top of the food chain, the global food chain, was essentially decapitated simultaneous with this transition out of the ice. And what I mean by that is essentially let's assume humans for the moment are the top of the food chain. Then what are we going to have underneath us? We're going to have the large predators. Then under the large predators are going to be the large herbivores. And what we see is that globally, 3/4 of the large predators and large herbivores disappeared at 12,000 years ago. And as far as paleontologists are able to tell, that disappearance of species was the most severe that this planet has suffered in perhaps as much as 5 million years. Definitely the most severe effects on the animal life of the planet in 3 million years. It just depends on how. There was 2 events. There was a 3 million year event and there was a 5 million year event. Which one of those turns out to be equal or to exceed the event of 12,000 years ago is yet to be determined, because the count of species loss is not completed yet. But at least 3 million and probably 5 million years is how far you'd have to go back on planet Earth to find an effect as severe on at least on the large animal life of the planet as what happened 12,000 years ago.